This one is I am woman. Yeah. Yeah, it's there. As I've seen with the other one.
So it's okay. Am I okay with the audio? Okay. Oh, it's okay. So I would like good evening also from me. Spyros Kallivokas, and I would like to thank Professor Vangelis Harmandaris for his invitation here, and Cyprus Institute for the hospitality these 2 days. I'm going to present you a part of my research that is focused on molecular simulations in the epoxy networks and the nanocomposites. But first, I would like to say some historical points. Yes, sorry. Okay. The first whoever introduced, at least even indirectly, the nanoscience and nanotechnology was the great physicist Richard Feynman. When in 1959 in Caltech, an American Physical Society meeting, he gave a lecture with a topic, "There's a plenty of room at the bottom," where he mentioned the advancement of science and technology if we'd be able to manipulate molecules and atoms. And in his opinion, one day humanity would be able to take the whole Britannica Encyclopedia into the head of a pin. Scientific community agreed that that was the historical point that nanophysics and nanoscience was birthed. Another historical point is the first mass product nanocomposite, which is, according to American Chemical Society, the bakelite, which was invented from the Leo Bakelite in 1907 in New York, when he invented actually the condensed polymer of formaldehyde and phenol. Due to its amazing electrical and thermal properties, it was a must for everyday household needs. Now, as you can see from the chart below, the nanocomposite market is huge, and it is linked with very specific, wide range of applications like military, automotive, packaging, electronics, and many more. I chose as a basis of my polymer to be epoxy, and the reason is that the wide range of application. Epoxies are the most non-vinyl commercial polymer, according to Stephen Malcolm, and due to the extremely solid state properties, although that is a soft matter system, and the wide range of applications, as I said, and before, you can see the charts from construction, civil engineered, environment, transportation. It is linked with the needs of everyday household and heavy industry. In the central image, you can see from BASF company an image of microscope with carbon fibers that are induced in a epoxy resin network. Now, as a monomer, I chose the Epon 862, as it is the industrial name, or the Jeff, as it is the chemical formula. The functionality is 2, and you can see that on the here. I don't know if it is okay. Perfect. The 2 benzyl rings in the center and the epoxides on the edges, left and right. And that's why it have the functionality too, because the 2 epoxides here and here. Now, this is the molecule, the epoxy molecule that we want to polymerize it, as we say in polymer physics. But in the resins, the epoxy resins, the polymerization happens with the help of another molecule, which is the hardener, as we said. And in order to happen the cross-linking process, this is the polymerization process. As a hardener, I chose this molecule, which is called DETA, as you can see that, and it has functionality 4, due to the 4 bonds that is able, excuse me for this, it has some inertia, due to the 4 hydrogen bonds that is able the amine types to create. You can see here the chemistry of the cross-linking process, and you can see that it is a 2-step reaction. First, the hardener, the amine type of the hardener goes to the epoxide, and they form the first step of the subnetwork. The epoxide edge opens and takes the amine, and then this product goes and links with another epoxide of another epoxy monomer, and that's why we said that we need 2 monomers for 1 hardener. Always the ratio is 2 to 1 because of the functionality 2 to 4. And to have the first subnetwork here after the 2-step reaction. Of course, this happens again and again in order to have a big network fully cross-linked. Now, the first step of the research was to study a fully cross-linked network and to explore the topology, the elasticity, the dynamics, and the structure of this network. We made 3 different networks in 3 different cross-linking degrees, 72, 82, and 92, with less than 4,000 of atoms. We put it as a force field, the Dryden exponential 6 force field, And under NPT conditions, we made some equilibration for more than 30 nanoseconds. You can see the final image of the network here, which is for the cross-linking degree 92%, which is more or less a fully glass network. And after that, we calculate the structure of the system. First of all, we show the density, how it goes as far as we increase the cross-link degree, and as we expect, it becomes more dense because we have a more glassy system. In the right, you can see the experimental values here. You see a range of values, and the reason it is that, and this is the difficult problem with these systems, that because we're talking about the family of resins, it's difficult to find exactly the same epoxy resin with the same hardener in the same cross-link degree in the experimental table, and to validate it with the same hardener, the same resin with the same cross-link degree. And that's why you see a range of values here, and it is the same problem in the rest properties. And that's why I have a range of values, experimental values all the time. But happily, the cross-linking degree, as it increases, it increases the density, and the values are very close. Yes. Also, yes, also the cross-link degree and the hardener. No, this is the problem. And in computational studies, this another problem is to find also the same force field, and of course the same parameters as I told. So it's at the end of the day, it's very difficult to find exactly the same system in terms of chemistry, in terms of cross-links degree, and in terms of force field if we're talking about computational systems. The second thing that we saw was the partial GFR and the coordination number for all the pairs for the network. And in order to see that, we made these plots here. You can see with the blue line the uncross-linked systems, which is totally melt, only the monomers in the simulation box. And with the red line, we see the fully cross-linked, about 92%. Sorry for this. With the coordination number that you see that on the inset of our plots, it says about how many times one atom, for example, the hydrogen first, sees again another hydrogen in a covalent bond. So that's why either both in the cross-link and the uncross-link, one hydrogen cannot see another hydrogen. That's why the coordination number here is 0, in contrast with other pairs. Of course, these are statistical numbers. That's why you see 1 point something. Of course, you cannot see 1 point something atom, but it's only statistical. We see some difference of structure, especially on the cross-linking atoms, on the cross-linking points where the cross-link degree happens. And after that, taking into account the partial GFR, we'd be able to calculate the theoretical XRD diffraction. Now, because of the small size system, due to the molecular simulation, meaning, we did that with 2 different methods. The first is due to the direct estimation of XRD, taking into account the structure factor. And the second is taking into account the partial GFR, as I told you before. The results are here. With the light blue line, you can see the direct estimation. And with the bold green and the bold blue is the method through the Fourier transform. We can see also here the difference between the uncross-linked, which is the green line. It has a more sharp curve here around the 1.2 Q space, which is about 5 angstrom, due to the due to the shorter and wider blue line, bold blue line, which is to the glass system, excuse me for this, due to the fully glassy system. And that's why, because we have a fully glassy system, and that's why we have a broader distances through the network. And that's why here you can see the wider and shorter XRD with scattering points. With the red and yellow, we can see the experimental values. Here again, we see the problem that I told you before, that is not exactly the same epoxy, but we weren't able to find exactly with the same epoxy, with the same hardener and an experimental XRD pattern. We see here, due to the size effects, some disagreement to that point of the plot. After that, we saw the topology and how the subnetworks and the functionality goes when the cross-linking process, when the cross-linking degree increases. We can see that the subnetworks, as we expect, they are decreased because of the fact that we have a fully glassy system as the cross-linking happen, and thus the subnetworks are becoming less and less because we have smaller groups that are attached to each other. The same physical meaning, with other words, is here. The tertiary amines are increasing because the bonds are linked with the other parts of the system, when the primary and secondary amines are decreased. And also we see the same here, that the functionality 4 of the system increases because we have a totally whole glass system, in contrast with the functionality 0 to 3. Functionality 0, I mean totally melt. Okay. Afterwards, we will calculate the elasticity of the system with 3 different ways. Again, we did it with 3 different ways in order to decrease the error bars because of the small size of the system. With volume fluctuations, excuse me, with tensile stress strain experiments, and this with 3 different strain rates and 3 different directions in order to take as far as possible to take out the errors, and with Parinello-Rahman method. As regards the volumetric method, as we know, we took into account the fluctuation of the volume, and from this we were able to calculate the isothermal compressibility, and from this to calculate the bulk modulus. As regards the Parinello-Rahman method now, we try to calculate the compliance matrix through the strains of the system in the equilibrium undeformed state for more than 70 nanoseconds of molecular dynamics equilibration run. In that case, these two parts are going to 0 because of the undeformed equilibrium states, and thus the compliance matrix takes that form and is more elegant and easier to solve it. Of course, we excuse me for that, I don't know how to, okay. Of course, we took into account the Lamé equations in order to take the bulk modulus and shear modulus from the Parinello-Rahman, because from the Parinello-Rahman and compliance matrix, we take only the Poisson and Young modulus. Here you can see all the values from all the methods for these 3 different systems, 92, 82, and 72. With bold, I have the agreements between the methods and the experimental. We can see, for example, that in 72%, we have an agreement in Young modulus and Poisson ratio between the stress strain and the Parinello-Rahman. Also, we can see that here, especially in the Poisson ratio, in the 82%. and happily also in the shear modulus in the fully glass system between the Parnello-Rahman stress strain and the experimental. We know that Parnello-Rahman method is a very sensitive method because it is a statistical mechanical formula and transfer the whole the errors that we may have from the thermal fluctuations and transform this error to the values. And after this, we have bigger errors for the error propagation. Why I'm saying all this? Because in some cases we can see extremely high errors like this. For example, it's a double of the value. And this happened because of the reason that I just mentioned, because of the very sensitive method that transfers this sensitivity through the fluctuation, and of course the very small size of the system. Also, we saw the dynamics of the system of this epoxy network with two different ways, with cooling rate and with WLF method, taking into account the correlation functions of the vectors. The cooling rate method that we did was to cool the system with 1 Kelvin per 200 picoseconds, which is of course brute force method comparing to experimental way that the people do in their laboratory, that they're doing about 1 Kelvin per or 10 Kelvin per minute. But the people that we are doing simulations will know that these rates, the experimental rates, are very, very slow, and we weren't able to see that. So in order to have reasonable times, we did that brute rate, and comparing, of course, the density versus temperature after that. We can see here the three different plots for the three different systems, and we can see the change of the slope here with the shaded region. So the width of two standard deviations. After that, we did it with a second way, which is the WLF method, taking into account the first and second Legendre polynomials of the epoxy segments OC and CH, in order to see how these two vectors of the bonds behave, and so to have a bigger image of the dynamics of the system. You can see here in the first and the second two polynomials Legendre that we take into account the vectors, and from these we take this parameter in order to parameterization this equation to have parameters like ALE, which is the libration, the parameter for libration of atoms around their skeletal bond, and the characteristic times on this libration, which is the T-seg and vita. And from these parameters to calculate the relaxation time, and from the relaxation time to calculate the TG. So here we can see all the results for the two different methods. You can see here the WLF for the two segments, for the two bonds, and here the cooling rate results. And I applied after that the Ferry approximation, which is an approximation that was introduced from the J.D. Ferry, who said that from these brute force cooling rate methods, we may have some errors, typically numerically speaking. And in order to minimize these errors, I applied the approximation, which depends of the error of the order of the cooling rate, in order to have the final values with the less possible errors. And of course, at the right, you can see the experimental values. Interestingly, we can see that although the brute force method, we have a quite good agreement with the cooling rate method, with experimental, I mean. In contrast, the WLF method, although that has some qualitatively good results. Quantitatively, it has some variance from the experimental values, and the reason is the sensitivity again of the method. As more sensitive is the method, the bigger error transfer to the final values, especially if you have small systems that we had. So, what's new at this point? For the first time in these systems, it was calculated partial GFR theoretical XRD and the glass transition temperature through the WLF method. And a more accurate, if you want, more accurate way to calculate the mechanical properties through the Parnello-Rahman method. And that leads us to this soft matter publication in 2019. After that, we took these epoxy networks and we filled them with graphenes in order to have nanocomposites. We filled them with 3 different types of graphene. Excuse me for this. 3 different types of graphene. Pristine graphene that you can see here, the ideal graphene, let's say. So as EPG, I mean the epoxy pristine graphene. The epoxy stands for the polymer matrix. EDG with defective graphene with holes randomly on the space with 5% atomic fraction due to the hole nanocomposite. And EGO epoxy graphene oxide, again with 5% atom fraction, and again randomly spared into the space of graphene. And the main target of this research was to calculate the interfacial fracture, or what the people that they're doing fracture mechanics, they see the interfacial shear strength. So we took these 3 different systems in 82% crosslinking degree, with bigger systems like in this time of more than 15,000 atoms, with driving exponential 6 as a force field, and we equilibrated for more than 70 nanoseconds with NPT conditions. Now, give me 1 second because I want to show you something. I don't know. Now, the problem, the phenomenon that we wanted to explore was this, that as it is here, the system, we tried to pull out the graphene, and you can see that with a yellow arrow. Of course, to keep it constant, to not moving the epoxy, and that's why we forced another force in the epoxy resin with a green arrow. You can see that, and so we tried to pull it out in order to happen the failure, the interfacial failure. Now we agreed on this assumption that if the graphene would be moved in a distance bigger than its unit cell that you can see on the left with the red arrow, if the distance of the movement would be bigger than this distance of the unit cell, then we agreed that we would have a failure, a local failure. And from this local failure, we'll be able to calculate the properties that we wanted. The first thing that we calculate, or the first thing that we were interested to see, was an interfacial constant that the people that they're doing experimental fracture mechanics, especially in macro scale, especially the people that are doing macro scale mechanics, they are measuring the Winkler modulus, which is a modulus that explore the interface of 2 different systems. Usually, this constant one can find on the geomechanics or civil engineer systems. So we were interested to see if this interfacial constant would be able to see that here. But here, of course, we have a molecular system and a different point of view. So we somehow constructed this Winkler molecular level constant with the way that I show you here. And we define this constant as local shear interfacial modulus. So depicts, let's say, the adhesiveness of the interface between the epoxy and the interface. And we calculate this for different temperatures and for the 3 different systems. We can see that the EGO, the epoxy graphene oxide, wins on this plot as it has better adhesiveness. And the reason is that because of the brushes, let's say, of the graphene oxide, the functionalization of the interfaces, they're working like mechanical blocking. They're working like brushes that they block with the polar groups of the epoxy. And as far as we try to pull it out, this is stacking and it has better adhesiveness. And that's why we can see bigger values for the blue triangles for the EGO. On the other hand, we can see that the pristine graphene in room temperatures disappears. We saw that it is totally, because of the totally clean surface, it has 0 adhesiveness, as you can see, and barely the EDG survive. The second thing that we were attracted on this problem is to calculate the time of the failure, and from the prism of statistical mechanics and kinetics. The first whoever did that was Zhurkov in 1965, who took an energy activation equation of Boltzmann-Arrhenius that you can see here, and he inserted the activation volume gamma, which depicts the space of the interface that will happen, the failure, and the shear stress that he put on the system, and he was able to calculate the time failure of the system. The rest parameters are the oscillation frequency of the atoms, which is in the order of -13 seconds, the TAF 0, and of course the energy barrier in the absence of stress, which is the U0, in terms of energy landscapes. How big or small is your energy landscape? Of course, easily can one measure the crucial, the limit of the stresses. If someone took the exponential to 0, can see the limit of the stress and the time that this happened, which in case of Zhurkov, the limit of times, it is the oscillation frequency of atoms. I mention this because we had somehow different picture of the system. The time, the limit time, the TAF lim that Zhurkov saw was about in the order of -13 on the oscillation of atoms. But we saw, at least in the epoxy pristine graphene, 2 orders of magnitude bigger. So we saw a numerical, let's say, disagreement. Here you can see the plot of the time failures contrast versus to the shear stresses that we put in order to pull out the system. And the first thing that someone can observe is that in the right regime of the plot, we have an exponential behavior of the system. And also we have a dependence of the temperature with the different colors at different temperatures. And all this behavior up to the sigma lim, which someone can see that with these here axis. And after that, the phenomenon changes and becomes linearly in log linearly. And it becomes temperature independent. All the colors are in the same line, and we have a straight line and not exponential. This also is a different picture of what Zhurkov saw. So we see another disagreement, not exactly disagreement, but another view of the image of the system. That's why we agreed to explore the system and the phenomena with the help of hazard plot analysis, taking into account the survival functions and the cumulative hazard plots from which someone could estimate the possibility of a failure through the rate, through the slope of the system. And so you can see here that depending on the plot, on the slope, you have a different type of failure. These two plots are the same. Their only difference is that the one is linear, and the second is semi-linear, semi-log. Someone could say that we have a zoom in here in the right, which is the whole this plot. This plot is a zoom in very small times, as you can see. It's a very, very here. And so putting different stresses, with different colors, we have different stresses. We see that we have different slopes. And so we can see for small stresses like this one here, for small stresses, we have a slope like this, which tells us that in some time, the failure will happen, sometime. But as we, excuse me for this, but as we put bigger stresses like this one, the slopes becoming more and more sharp, like the second plot that we have here, which is, as I told you, a zoom in into the very small times. And as we put bigger and bigger stresses, we have a totally sharp slope, which depicts that the possibility of the failure is 100%. The failure will happen directly. That's why you can see very small times. It means that as far as you put brute stresses, the failure will happen directly, very, very fast. So this, and also these behaviors, and also that we took the same behavior from what we saw before, that from these hazard plots, we saw that we have an exponential, somehow exponential behavior. And after that, an independent, colorly speaking, independent in terms of temperature and linearly with an order of minus 0.5, which is a square root. So all these results lead us to the idea that maybe finally the time failure is not only one parameter that Zhurkov introduced, but maybe it can divide it in two different times depending on the stress that you put. And that's why you have the different behavior for the two different regimes. So what we proposed is that depending on the stress, if you have stresses smaller than the sigma lim, you have an exponential behavior of the time of the failure, adding, of course, the numerical difference, the tough limb that we have in contrast with the Zhurkov. And in the second regime, we have a linear response, which depicts the acceleration motion, and which says for the, as far as you put high stress, it has an acceleration motion because of the totally destroyed interface. And this we can see here for all the three different systems: the epoxy, pristine graphene, defective, and graphene oxide. We see that the three-hole systems have this exponential behavior, and after that we have this linear behavior. Again, this here, the proposed equation that is the result of the parameterization, of course, okay. And of course, we were able to calculate the effective energy barrier versus the shear stress for epoxies for the three different systems. And you can see also here the different adhesiveness that depicts on this plot that you have in the epoxy pristine graphene has a very small energy barrier in terms of energy landscape. And the bigger energy barriers, and of course, even bigger in the EGO. Here we see a nonlinearity, which is due to the different segmental mobility of the polymer that affects the mechanism of the reinforcement because of the OH groups. They are working as a brushes, let's say. Now, for stresses which are smaller than the sigma limb, also someone could be can calculate the sliding velocities can we see here? I don't know what is this. For the three different systems, the first is for the EPG, the EDG, and the EGO. And of course, we see here in terms of physics, again, the difference of adhesiveness. We have a very poor adhesiveness, also almost zero. And that's why you can see that the graphene comes out with almost zero stress. And that's why the simulation calculations contrast with theories, they're having this error. We saw that due to the very smooth and clean surface, the graphene somehow swim, let's say. So the adhesiveness is zero. In contrast, the defective graphene, due to the holes, it has some better adhesiveness and has some better agreement with theoretically and simulation values. But of course, the best adhesiveness is the EGO system, when we can see a stick-slip phenomena here. And of course, it has the better agreement between the theoretical and simulation. Yes, yes. I mean, yes, yes, of course. It is this formula downstairs. Sorry for this. It has some delay, the laser. Okay, you can see here the velocity. Okay, if you know the TAF F, the time of the failure, and you know, of course, the delta Rx that you're putting, you're able to calculate via hand, like a homework. Yes, so these are the theoretical values. Yes, exactly. The theoretically value of the velocity, because here you can see the velocity, and the green are from the simulation, and we have these big errors, this big distance, let's say, of the value, big through they're totally swimming. It was amazing. And we saw some other papers that they're exploring other problems, but with graphene as interface, and they show also this, how can I say that, the zero adhesiveness, that the graphene, it has zero, it doesn't cooperate with the rest polymer matrix. And also some colleagues from the group also show that, also in PMMA, I think. So here I have all the parameters for the three different systems, but someone may be interested in order to have a totally numerically image for the systems. We see the energy barrier, it is higher here in the absence of stress in the graphene oxide because of the better adhesiveness, as we said before. We have the smallest gamma value, again on the EGO, which depicts also the same thing, the better adhesiveness. Why? Because as far as you have better adhesiveness, the failure will happen in a very concrete point. And so the gamma value, which says, sorry for that, I didn't do that. Is it? Okay. And so you have a very specific point of the system that the failure will happen. And so the gamma value will be smaller. From the other hand, the EDG, the epoxy defective graphene, it has the bigger because of the defects. And if someone pulls out the defective graphene, because of the defects that are randomly on the space, the crack, let's say, propagation will be randomly. And so the gamma value will be bigger. I mean, I don't know if I'm clear. Again, the same physical meaning with different words we can see in the rest parameters like sigma limb and tough limb. In sigma limb, because of the better adhesiveness between the polar groups and the OH, we have bigger, we need bigger stresses, and so the sigma lim is bigger. I don't know what's happening. Again, we have, because of the better adhesiveness, we have the smallest tough limb, or the smallest difference, let's say, between the Zhurkov predicted and our simulation. It would be, in terms of physics, someone could say that this depicts the inertia of the system. As far as you have smaller values of tough limb, you have the system is more, how can I say that, more alert. It wakes up earlier to the stress that you put. And in the last two columns, we can see the first parameter that I told you about the molecular Winkler image. And it's very interesting. In epoxy graphene oxide, our value that is very, very similar to a Winkler modulus of PMMA and graphene that of a publication of Galiotis did in 2017. Here I have a movie that depicts what I told you all this time. As Confucius said, you know, one image is 1,000 words. I have colored one carbon atom with yellow in order to have a reference point. This is for the epoxy graphene oxide. And we see this stick slip phenomena for stresses that they're smaller than the sigma limb. I pull it out, it breaks, then it stacks again because we have some blocking again. I pull it, it stacks. And this is an image of that our calculation, although that they start from a very local assumption, they are globally validated, and so they are independent of the local assumption. This is very interesting. So, what's new here? We made a molecular recipe in terms of local interfacial shear modulus, or what I call molecular Winkler modulus, and we extend the Baz equation, taking into account the bigger stresses, and this leads us to a publication of the physical review 3 years ago. Now, my wish, my willingness is to extend this method that we did to explore more geometries and more chemistry and other chemistry and other chemical systems, and of course to do that collaborating with experiments and mesoscopic methods like finite element methods, in order at the final chapter of this problem to see if from these things we'd be able to see the crack propagation from the Griffith theory, and if this methodology that we made is so powerful, let's say. In that point, I would like to thank Professor Theodorou and Dr. Aris Gouros that we did these works, and of course, Dr. Stefanos Anogiannakis and Professor Michalis Kavousanakis for the helpful discussions, and of course, Evgenidis Foundation for the scholarship that I had in my PhD. Thank you very much.
Okay, so thank you for this presentation.
You're welcome.
Actually, I have two questions.
Yes.
The first question, if you go to slide 22, when you compare the theoretical, it's not theoretical, sorry, the
22?
Yes, here.
Here, maybe?
Yes, here.
Okay.
Okay, so here you compare three different methods. I guess two from equilibrium, which is the volumetric and the
Exactly.
And the one it's non-equilibrium.
Exactly.
From stress strain.
Exactly.
So I'm just curious about the condition that you are using the stress strain methodology that you use to compute Young modulus and the Poisson's ratio in order to compare with the other method. Because, for example, what is the strain rate that you are used in the stress strain?
As you can see, we did it with three different rates, from 70 up to from 7 to 9 in second -1. So we took these three strain rates, but we saw that we estimate on the 10 in order of 8. So the answer is 10 in the order of 8. But we did it with three different rates.
And the results for these three different rates are the same?
No, we have some variations, but we agreed that in the third, which is it's not appear here, the 5 times 10 in the order of 8, it's the best rate. The best in what terms? In terms of in the time of the calculation, it's not 3 months for each calculation.
Which one is more close to the for example, Parinello or Rahman? Which strain rate?
The 10 orders of 8.
8.
Yes, yes.
Yes, it's equilibrium.
So I'm saying again that we did it with three different strain rates, but after that, and of course I have the values if you want to see, but after that, we saw that combining the calculation time in terms of reasonable time of calculation and reasonable values, the best is the 10 of orders of 8, and the result that you saw were 10 in the orders of 8.
Okay. Just another question.
Yes.
If you go please to slide 23.
Yes.
So you compute the stress after you apply the force on the
here,
right?
Yes.
Here. So sigma equal F over the average area, right? So just my question: how is sensitive the computation of this coefficient G? If you increase, for example, F, or if you change F, for example, do you get, for example, the same value of this G? So, for example, now you have. If you have a specific value of F, and then from this F you compute the delta R, right? And then from the ratio you get G. So my question: if you change F, for example, you will get the same value of G. How
but if I understood right the question, the answer is this is what we're doing. We change the shear stress, and thus we change the F, right? Yes, exactly.
So you apply force on the graphene.
Yes, exactly.
And from the force you compute sigma.
Exactly.
Okay, and then delta R and then epsilon, and then you will obtain G. Okay, if you change F now, if for example you use 1.1 F, for example, you increase by 10%.
But that was the way that we calculate how can I say that? We changed every time the F.
So this is from the slope.
Excuse me, this is?
This is from the slope between sigma and epsilon, not the ratio between sigma and epsilon.
Do you use a constant force?
No, we change it every time.
So is it calculated the slope of the stress?
No, we applied in the lamps different forces every time.
Yes.
And from these different forces, we calculate the sigma that you see here.
Okay, and you calculate different epsilon.
And from no. Before we go to the epsilon, that's why this is how we calculate the sigma. Is it clear? This?
Yes.
Okay.
So you have different values of sigma.
Perfect. Okay. Then from this we have some distances different.
Okay.
Now I'm going to the strain. Okay, to the epsilon. We have some different distances, and we took the mean average every time.
Okay.
And taking into account also the closest distance between one graphene to another, delta Z, exactly. That's how we calculate the epsilon.
So now you have also different epsilon.
No.
You have different force.
No, I don't have different force. The strain it depends only on the movement. Okay, so every time you change force, so you have different sigma. Okay, then you have then because of the different how can I say that, of the different sigma, you have the movement. Okay.
Okay.
And so you're able to calculate the delta Rx, and from that the epsilon.
Okay.
Is it more clear now? No.
Okay.
We'll discuss later. Okay. Okay.
Because I cannot relate one value of epsilon
Yes.
to different value of sigma. So you say that you have different value of force, right? So this means that you have different value of sigma. Okay. Okay.
Here?
Yeah, experiments, they don't use and what was
The medium, I mean, you mean the hard? No, they don't use solvent. They put the experimental way, you mean, right? In the experiments, they take how can I see that? They take the resin as a melt, as a solvent, okay? So we could agree that this is the solvent, and we put and they put on the resin the molecules of hardener, and they mix it, and they increase the temperature, then they decrease it, and they put. Yeah, I told you they have some temperature changes, and you have the cycles, and precisely you have some cycles of temperature. You go very high and then you cool it, then you increase it, then you cool it again and again. This is the experimental way. So you have change of temperature. If the solvent somehow solvent is the resin, they do not mix anything else. They mix only these two things. Yes. We didn't show monomers. We saw a fully glassy system with the interface.
yeah.
Mm-hmm. If we show hydrogen bonding, you mean? I'm trying to. If we show any interaction, you mean, in terms of chemistry? Of course, they may. How can I say? Interact with van der Waals, which are the weakest. But because of the weakest, the van der Waals can break very easy. Of course, yes, but all these are very weak in contrast to the force that we. No. Generally speaking, they are strong, but the coulombics that they may be appeared here, they are very. How can I say that? You have some polar groups that they are spared, and so the total amount of the interaction that they may have, due to in contrast versus to the brashes of the OH, are very, how can I say that, statistically speaking, very small due to the force that they induced. In that way, I mean, of course, Coulomb are very strong. And so they cooperate somehow. Sorry? Yes. Yes. From this. From the energy barrier, you mean? Of course, it's another step, but physically, in terms of higher stresses than the sigma limb, I cannot imagine how these interactions would be so bigger than because you show an acceleration. It's like a fluid, and at that here at the right regime of the plot, you see that the system does not understand anything. It has so much stresses that goes like a fluid. It has an acceleration motion, and that's why I answered to Sisem, right? To Sisem that and to you that of course the Coulomb and other interactions maybe appear, but especially on this regime, they're so brute the interactions in mechanical speaking interactions that it doesn't feel anything. It just goes, and that's why it goes acceleratedly, and that's why we show the sliding velocities. As a separation systems, you mean for like filters? Stationary phase, what do you mean? I do not fully understand what you mean. Yes? For better adhesive, I mean, for coatings, for if you want to have a better cooperation for between polymer matrix and interface, for better coatings or for better collaboration for the load, for the mechanical load.
Thank you.
Thank you also.
Thank you so much for the presentation.
You're welcome.
One comment on the beginning of the presentation when you reported some factors you showed
Here?
Yes.
Change. Deltas, you mean? What do you... At the difference of the density. The fracture energy. For example, if you want to see a void in your network, right? To the epoxy glass network without this nano. Okay, yes. To see the rupture. This is what we're trying to see now with a PhD student. Generally speaking, via the molecular simulation, it's extremely hard this, because you have to introduce in some way the rupture of the bond. And with the classical force fields, this is, it's not very easy speaking. We have also the advanced force fields like reactive force fields that up to one force, they break the bonds. But unfortunately, the computational times are extremely slow in order to see a rupture, like in order to have the beginning of a crack propagation, let's say. The cross-linking process? For this process, because the cross-linking process by itself is a very difficult thing, okay? I proposed that, and finally, this is what we did, that we followed an already algorithm that is on the that has proposed about 2010, if I'm not wrong, from Lee and Strahan. And so this algorithm that we followed also, which is based on geometrical criteria and energy minimization, and follows a molecular dynamics route in very high temperatures in order to be as fast as possible. It takes about, at least for small systems like 4,000 atoms, it took about some hours, let's say. But for bigger systems that we see now with the PhD student, it takes about half a day or like that. So again, it's very logically time. You're welcome.
Spyros, thank you for the presentation.
You're welcome. Thank you.
I have two questions. One is very generic. It's, whether you know, you presented three methods for calculating the mechanical properties, volume fluctuations, and the stress strain. Is there any general way, let's say, to say that one is better than the other, or for your particular?
For these reasons, I present you here all the results. In my opinion, at least, I think that the stress strain is the best in terms of reasonable calculation, time in terms of calculation, and in terms of experimental values and other comparison like volumetric and Parnell-Rahman, because in Parnell-Rahman method you're waiting about a month or longer than month, and your results, as you can see, are very sensitive. So in my opinion, the best is stress strain, because it's very reasonable in terms of time, calculation time, and the results, as you can see, are quite good in terms of quality and quantity comparison.
Why the frequency is not
Monotonic.
Yeah, for the stress strain. Generally, it's more accurate. It's dependence, 100%.
Yes. You mean that it becomes bigger in the 82 and then becomes smaller, larger and larger. Of course, you have. It's not. How can I say that? Of course, statistical errors may come into the values, and you see some. How can I say that? Some disagreement like this that's not monotonic. But from the other hand, someone else could say that taking into account the error bar, it's not so big the difference.
So it's just
Yes, because also we can see that from the error bar. I mean, it is how can I say that? It is 3.3. Yes, of course, taking into account the error, it is 3.7. So we can say that, and also the last, it's of course, and that's why I mentioned again and again in my presentation that we did all the properties with 2 or 3 methods, because we had very small systems. The one question could say, someone could say, why you did from the starting point bigger systems? Because I was afraid of the very long and very slow calculation time of the polymerization process, of the cross-linking process, because in the starting point we didn't know how much time it will take us, and how much difficult it would be to calculate all this heavy in terms of molecular chemistry, these heavy systems. We have nitrogens, oxygens, polar groups, interactions that may arise like Coulomb that you said, or whatever else. So it was a reason of, how can I say, to be more conservative, because we were more conservative, we put it smaller systems. And that's why we have these statistical errors, but from the other hand, we took more methods.
So on this statistics part, I don't think, I'm not sure whether the observation is right.
45, okay.
Yeah, you have this limit.
Here?
Yeah. So it breaks, you mentioned that it breaks and then it's stuck again.
Stick slip from, yes, yes.
And then it breaks again. So does it start at the same point exactly?
No, this is random. I mean, it depends. It depends of, you pull it, you put a force or a shear stress and you pull it out. This, as we can see from the video, it breaks. The point that you have this failure, the stress that you put it is interfacial shear stress, and this is the strength, interfacial shear strength. After that, the graphene starts to moving, okay, after the failure. But randomly, when the polar groups and the brashes, I mean, metaphorically speaking, the OH groups of the graphene will meet again, the graphene will stop again. So it's a stick slip. So the answer is not. The answer is no. It will not stop exactly at the same.
Because I noticed that this yellow atom.
It comes again.
In the position.
No. It is a video. I mean, if you see, I cannot show you now, but is first of all you have the periodic boundary conditions, and second, it is the video that stops.
Yeah, it's a video.
Yes. Okay. You can see it breaks.
It's glassy.
Yes, it is about 82% of cross-linking degree. So it's totally glass.
Thanks.
You're welcome.
I will ask again.
Okay, thank you. Thank you. You're welcome. Thank you.